Welcome back. We're going to continue talking about the atomic theory today. If you remember from our last video, we had a couple of models of the atom. We had the Dalton billiard ball model. If you remember that, that was proposed by John Dalton. This was the first atomic theory based upon experimental evidence. He imagined atom just being a sphere, and different elements had atoms of different sized spheres. The important thing is, he said, those things are not divisible. It's as small as you can get. Then we had J.J. Thompson with his plum pudding model. If you recall, this was J.J. Thompson. And he envisioned the atom as still being spherical, but having this positive matrix of protons. And for every proton, there was that many electrons. So if I had 5 protons, there'd be 5 electrons. He learned that atoms are made up of small subatomic particles, smaller particles than the atom. Now, we're going to advance that just a little bit today. We're going to talk about Ernest Rutherford. I'll read this sentence or two to you, but it won't make a whole lot of sense until I do some explaining. So under the direction of Ernest Rutherford, Hans Geiger and Ernest Marsden subjected a very thin sheet of gold foil, so this experiment became known as the gold foil experiment, kiddos, to a stream of positively charged subatomic particles, alpha particles. They found that most of the particles passed right through the sheet. And from this, Rutherford concluded that the atom must consist of mainly empty space. Now, what does that all mean? Well, let's draw a picture of Rutherford's gold foil experiment and see if maybe that will help us in our explanation. Okay, kiddos? So, we're going to draw right here a circle here. And this surrounded Rutherford's experiment. It was made out of zinc sulfide, which would fluoresce or glow whenever it was struck by an alpha particle or some ionizing radiation. He had a block made out of lead with a hole drilled in it. See if we can draw a block made out of lead with a hole drilled in it. Let's see how I do here. There's my hole. There we go. Does that look like a block made out of lead with a hole drilled in it? Sort of, kind of. Inside this block of lead, so pretend you have vision better than X-ray vision, so you can actually see through lead, we had a radioactive source back here. And this emitted what we call alpha particles. I'm just going to give you the symbol for alpha here. And you need to know that they are positively charged. Okay? Now, when these particles, this radiation, was emitted through this hole, it went straight across, and it would cause the zinc sulfide screen to fluoresce directly across from the opening in that lead block. Well, Rutherford directed his assistants, Hans Geiger and Ernest Marsden, to put a piece of gold foil between the block and the zinc sulfide screen. So this is going to be a piece of gold foil, very, very thin. In fact, I'm going to show you a video that someone did illustrating, or showing actually, Rutherford's gold foil experiment. That'll help, I think, clear it up even more. And when they did this, they needed to do it in a pitch black room, what we used to call photographic dark rooms. You couldn't see your hand in front of your face. And the reason they had to do this was so that they could see this screen fluoresce whenever it was hit by an alpha particle. And Rutherford asked Geiger and Marsden to count how many times it would hit that zinc sulfide screen. Now, when they were doing this, they noticed some flashes of light at angles from where they were emitted. So on occasion, they would get a flash at an angle. The beam was deflected somehow, maybe over here. Didn't happen very often. Almost 100% went straight through, but on occasion they would get a deflection. So they talked to Rutherford and they said, "Hey, Dr. Rutherford, we've seen some deflections," and Rutherford wanted to know, well, what angle? What was the extreme angle of those deflections? So he had them look the backside of the zinc sulfide screen. And sure enough, on even rarer occasions, some of those alpha particles would cause the backside, and some were even right back towards the source. They'd cause that zinc sulfide screen to glow. And Rutherford couldn't figure out what was happening because using the Thompson model of the atom, who, by the way, J.J. Thompson was the mentor of Ernest Rutherford. And so Rutherford really held Thompson in high regard in his model of the atom, but using that model of the atom, he couldn't explain why these alpha particles were being deflected. Remember, the alpha particles were positively charged, and for some reason, they were deflected at strange angles. So he finally came to this conclusion. Remember, atoms have positive and negative charges. So what if all of the positive charges were concentrated in a very, very small, dense center of the atom, which he ended up calling the nucleus of the atom. So that was positively charged. And the electrons, on the other hand, were huge distances away from this nucleus, and of course they had negative charges. So between each nuclei, folks, Rutherford figured out there is a huge distance relative to the size of the individual nuclei. That distance was huge. Well, how did he come to that conclusion? Well, remember what happened to most of these alpha particles. Yeah, close to 100% went straight through. So these tiny spheres right here represent alpha particles here, here, and up here. Most of them would go straight through the gold foil and continue on, and they cause the zinc sulfide screen to fluoresce. Now, if the nucleus, which is positive, remember folks, if the protons were concentrated in the nucleus, what if an alpha particle came close to the nucleus? Remember, it's positive also. Don't like charges repel? So the closer and closer it came, wouldn't it be deflected at an angle? What if it came head on? What if it hit the nucleus head on, so like this, boom. As it got closer, wouldn't it be repelled backwards towards the screen? Yeah, now the only way that this would happen is if there was a large distance between the nuclei. Remember, most of the mass of an atom is made up of the nucleus. Almost all of it is. So, what's between these nuclei? Well, you'll say there are electrons between these nuclei, but those electrons are really, really small. And it turns out this distance is so huge, Rutherford concluded that most of the atom must be, or most of matter, must consist of empty space because of that big distance between the nuclei. And he was able to determine that because most of the alpha particles went through undeflected. That means they didn't even come close to a nucleus. On a rare occasion, some of them would come close to the nucleus and be deflected at a strange angle towards the zinc sulfide screen. Some would hit the nucleus head on, a very, very rare occasion, and they would be deflected right back towards the lead block. So we end up with another model of the atom, the Rutherford model of the atom, kiddos. And so it consists of a nucleus where all the protons, and we're going to learn neutrons, are located, so it's positively charged. And then surrounding that nucleus at huge distances were electrons. Now, he didn't know too much about the orbits of these electrons or exactly where they were. He just knew that they were outside of the nucleus. So we end up with the Rutherford planetary model of the atom, where the protons and the neutrons are concentrated in a very, very dense center called the nucleus. It has the protons and the neutrons. And these electrons orbited the nucleus at huge distances away from the nucleus. So the distance between two nuclei, most of the mass of matter, is huge. So matter consists primarily of empty space. And Ernest Rutherford discovered that. All right, that's good enough for today, kiddos. Talk to you soon. Bye-bye.